Thank you for joining. Let's wait for a couple of minutes for others to join, then we'll get started. Meanwhile, I have some links here. If you want to run this tutorial on your own or the workshop that I'm going to conduct today, you can scan the QR code, or there's a link, go.lakefs.io/TMLS. Uh, but I'll walk through the instructions later on. So just hang on. Once again, thank you for joining my workshop. I'm going to focus on machine learning reproducibility at scale. So it's a challenge with machine learning is like using different data set. And when you're running the models, you end up having different versions of data set, and you want to see what data was used for to train a certain model. So that's the topic for the workshop today. So I'm going to run this workshop on my local laptop, but also you can run at scale, let's say in any Spark cluster or Databricks cluster. So I'll show you that. Just for introduction, I'm Amit Kesarwani. I'm solutions engineer with LakeFS. LakeFS is the open source project. The company behind that is Treeverse. So I work for a company called Treeverse, but the project name is LakeFS. The challenge in the day of the life of machine learning users is managing different data sets. So people a lot of time have a huge data set which they cannot copy to their laptop when they are building models or training their model and when they are testing it. So what people normally do is they take a sample from the data sets. So you might have terabytes or petabyte of data which you cannot keep on your laptop. So you normally take sample of that, and then you train your model, and then version. A lot of time you might end up having different versions of data set, and it becomes very tedious to manage those different versions when you're running locally, even in the, let's say if you keep in the cloud storage, even then it becomes very difficult to manage different versions of data set to train different models and see what data version or data set was used to train certain model. And when you use different parameters to train different model, you might end up using different data sets, and that becomes very challenging to manage all those different versions. People end up copying everything and maintaining everything in different folders. So there are many ways people try to do this manually. And the requirement for maintaining those versions, why do you need those versions, is one is the reproducibility purpose. Like if you are running models 1,000 times and training those models, at the time you want to see, let's say, which model produced the best result, and for that model, what data set was used. So that becomes very important to reproduce that using that same data set. Let's say you train a model and it produced the best result, like let's say 2 months back, and now you want to use that version of data set. What people do is normally they just sample the data, they have different versions of data, and the reason that people need different data sets is for reproducibility purposes, like managing those different versions is for reproducibility, so they can go back and see what data set was used to train what kind of model. And also for collaboration purpose, like if you are maintaining different versions and you are collaborating with other team members, then you want to have those data sets available to other team members also easily. So if you try to version things locally on your laptop, first of all, you have the storage limitation, and second, you won't be able to share that easily with your team members. Another reason to version your data set is for auditing and compliance purpose. So let's say for any regulation purpose, the regulators might ask what data was used to train that kind of model, when you produce a certain result. So you have to maintain historical data set and different versions of data set in case if the auditing and compliance requirements come into play, as well as the requirement for versioning is for documentation purpose. And when you're running different experiments, you might run with different versions. So that also is very important to version control everything. So Jen, I'll pause here. Everything looks good so far now. I'll just see any questions. Okay, he's saying they enhance the size. Only challenge is that if I put into a slideshow mode, like we lose, it goes into the loading mode. So let me see if I can do something to increase here. Okay. So let's talk about how LakeFS helps into versioning your data set. Let me So in this case, like LakeFS sits on top of your object store. And when you are using a front-end tools, any tools that you use, you can directly go to the object store or go through the LakeFS. Just to make sure that LakeFS currently works for any types of object store, whether it's any cloud storage, for example, S3 or Azure Blob or cloud or Google Cloud Storage, as well as any on-prem object store, which is S3 compatible. What that means is like there are other on-prem storage like MinIO or Dell ECS or storage grade from NetApp and Pure Storage. So all those multiple storage companies have on-prem object store also, which are S3 compatible. So we LakeFS works on top of that object store also. And LakeFS provides like a Git-like interface to your object store. If we have used the Git product for software version control, LakeFS works very similarly to version control your data set. And I'll show you how it works locally also, so you can work locally in case you need to clone the data set locally. So I'll show you that piece also, but normally we work on top of the major object stores. And the way it works is, let's say if you're using S3, normally you use S3 and you specify the bucket name and the collection or the subfolder or prefix within the bucket. And that's how you normally access your data set. But when you use LakeFS, in LakeFS, we have a concept of creating the branches. So you can have production branch data set. You can create experiment 1, experiment 2, and so on. You can have multiple experiment branches of your data sets. So in this case, for example, when you access data through LakeFS, you specify the branch name also, along with, let's say, a bucket name or the repository name, and the branch name, and then you have your collections and the file name or the prefix. If in LakeFS, you similar to like Git, you can create multiple branches. If you're running thousands of experiments, you can create different branches for each experiment and run those in isolation without impacting the other experiment you're running. So that's a kind of major requirement, like running, one of the use cases is running things in isolation without impacting other users. So in this case, you can have your experiment branch so that you are not impacting your production branch or main branch. So that's how the LakeFS works at the high level. So basically, LakeFS is like a version control for your data set, basically using data as a code, similar to your software development. And the way it works internally is, let's say this is your storage bucket. LakeFS does not store the data. Data will stay in your storage, and you control it, you manage it. But LakeFS sits on top of that storage. And we don't need read and write permissions also to your data. If people are concerned about LakeFS accessing the data, then we don't read and write. We only maintain the metadata about those data files that you store in your storage bucket. Only thing is LakeFS sits on top of that to manage, do the version control. So in LakeFS, as I mentioned earlier, we have concept of the branches similar to like Git. So you have your main, let's say main production branch in this case. And every commit in LakeFS, when you commit any data set, is basically a set of pointers to those files. So let's say you have these files, these 4 or 5 files here, and this metadata at the time of commit when you do, it just set up pointers to those files. So LakeFS only stores the metadata information. We don't read and write your data files. So we don't need access to that data set. We just need to get the information or metadata about those files. And those metadata is basically a pointers to those storage location to those files. So that's kind of commit we maintain in LakeFS. So let's say in this case, for example, these were a set of 5 files in the particular commit. Now, let's say if you are changing a file, in this case, let's say you change this particular file, in object store, normally you don't update a file, you delete a file and then you create a new file to replace it. So in this case, let's say you commit, and the new commit, now you are pointing to these set of 5 files. So the previous commit points to the previous 5 files, and now the new commit points to the new set of 5 files in this case. And this gets more complicated if you have millions and billions of objects. So we maintain all those data set, all the pointers for each commit information. And when you create a new branch, so let's say you want to train your model in a separate branch without impacting your production branch or production data set, you can just create a new branch. And creating a branch is a millisecond operation in LakeFS. It doesn't take any additional time to copy any data. We are not copying any data because we just maintain a set of pointers. So anytime you create a new branch, whether you have terabytes or petabytes of data, it will take a millisecond to create a new branch. So in that case, if you're running thousands of experiments, you can easily create thousands of branches from your production data without impacting your production data set. If you make any changes in the new branch, that will be only stored in that branch only. So you're not changing any commits in for the production branch, but only any changes you are doing in a separate branch, it will stay in that branch only. So the question comes up like as we maintain these different commits, different branches, these number of files will continue to grow over time. Because when you delete any file, for example, in this case, it's a soft delete, we don't hard delete. So in case you want to go back, you can roll back your changes. So what we do offer is something called process called garbage collection, where you can define your retention policies in LakeFS and say, for my production data set, keep it for, let's say, 7 years or 5 years. For my experiment branch, any data set that you create for the experiment branch, specific to experiment branch, for example, you delete that after a week or after 6 months. So you can define different retention policies based on different branches. And system LakeFS will automatically clean that your storage. So a lot of time when people are running an experiment, they make a copy of data set, they forget to delete the data set, and the storage keeps on growing. So by using LakeFS garbage collection process, we automatically clean that data set. So all the historical data, we automatically go and delete and clean that. That way you end up eventually saving the storage. So there are 2 ways you are storing storage. One is whenever you create a new branch, we don't copy any data, we are just using a pointers. So that's how you save the storage without copying any data. Another time you save storage is we automatically do garbage collection. We clean your storage so that you don't end up having a lot of storage utilization. So that's how LakeFS works internally. And anytime, let's say you want to refer back for ML reproducibility purpose, you can go back to any previous commit and see what data set was used at that time. So let's say if you are maintaining in a production data set for a year, within any commits, any data set you have in the last 1 year, you can go back and refer it to that and see what data set was used to train your model at that time. I'll pause here. Let me see if there are any questions. 1 second. Somebody is saying if I can show the QR code once again. So I will show that. It's coming up very soon in next slide. one more slide after this. So I'll show the QR code, and then we'll start doing the workshops. So LakeFS, as I mentioned earlier, it works on top of the object store, but LakeFS can work locally also. So similar to like Git clone, where you can clone the Git repository locally, you can clone your data set also locally using LakeFS command line interface called LakeCTL. So you can clone this locally. Of course, when you have terabytes and petabytes of data, you're not going to clone the whole data set. So you can specify within your repository and within your branch what folder, you can pick a folder and clone that. So you don't have to clone your terabytes or petabytes of data. So let's say if you're running an experiment, you create a separate experiment branch. Within that, you might have smaller data set, which you can clone locally to train your model and work a data set locally. And if you make any changes locally also, so for example, let's say you delete a file and you add a new file, again, we just maintain those pointers to those files. So if you make any changes locally also, and when you commit, we also commit that changes to the repository online. So any changes you do, file and commit any changes locally, it eventually goes into the object store also. So everything gets committed to the object store. So even if you delete everything locally or lose everything locally, you will have all those changes in your LakeFS repository in your main object store also. Okay, so that's very couple of slides to explain how LakeFS works. Now let's go into the actual tutorial and workshop. So I'm going to show like two tutorial. And if you want to run this on your own, you can just scan this QR code. There's a link also here, go.lakefs.io/TMLS. So you can, if you can't scan the QR code, you can just go to this URL here. And let me just click and I'll show you what this thing looks like. So this is our samples repository, Git repository for our samples. The code that everything that I'm going to run in the workshop today, it is available here in this repository. And everything I'm using is open source. So if you want, you can run this easily on your laptop. And in the tutorial too, I'll show how you can run in the cluster environment also, in the large scale environment. So here, this is within this our LakeFS samples. There are multiple examples here, but today I'm going to use this image segmentation local example. So I'm going to run everything locally here. But if you go into the main, you see a lot of different notebooks and samples that we have. So today I'm just going to focus on this standalone example, and within that is this image segmentation local. And that's what the link will take you directly if you scan the QR code and use this link. Next thing is, like, if you want to run this locally, you will clone this repository. So you will find the instructions here in our Git repo also. So you don't have to type in all this information here. You can just go here and just copy this instruction set from here and clone the repository here. Go to that particular folder. It looks like there is just might be some question. No. Okay, so you can just clone this repository. I already cloned this repo on my laptop. And once you clone after this, you run everything in a Docker container. So so the requirement is to have Docker installed on your local machine. So right now I'm running Docker, and once you run this Docker Compose up, what it will do, it will install lots of multiple things. One is LakeFS, which I'm going to use for the workshop. Also an object storage called object store called min.io. So you don't have to use your S3 or any other cloud object store. Min.io will work locally on your laptop. So everything is anything required for this workshop is packaged together in this container. Plus Python, Spark, and I'm going to use Jupyter Notebook for the workshop, and Java JDK, and anything else required to run this demo. So once you run this, it will spin up these three containers. So this is a group of containers, and within that, you'll have three containers. One is for Jupyter Notebook, which I'm going to use for the demo. LakeFS also running in a separate container. Again, LakeFS is open source, so it's here I'm running the open source version of LakeFS. We have commercial offering also, but for this workshop, I'm using the open source version. Plus MinIO, as I mentioned, the object store that I'm going to use for the for this workshop. So once you run this, it will create all these three different clusters. And if you have any conflict with the port number, you can change in the Docker compose file, and you can change the port numbers. So here, this is the Git clone I did, the repository I cloned. This is the folder within that. And here you have a Docker compose file and Docker file. If you want to customize and make changes, you are free to do it on your locally on your laptop. Okay, so now once you finish this, you have all the full workshop running in a container environment. Let me explain what I'm going to show today, or what we are going to do in this workshop. So I'm going to use the image segmentation use case, where I'm going to utilize the images to find certain things in the images and create different versions of data set also. And those versions of data set will be stored in LakeFS, and the data is stored in this case, in local MinIO object store. So for this workshop, I'm using this data set, which is available on Kaggle, and it's open source, like freely available data set. And with this container, I also included this sample data set, so you don't have to download this data set. It is already there installed as part of the container. But just I'll walk through what this data set looks like. So this was the challenge run by Airbus a few years back to find certain images or find ships in a satellite images. So they provided a data set which is about 200,000 satellite images. So this is how it looks like. And within that images, you have to find the ships using machine learning models. So that was the challenge they ran. And there are a lot of participants in that, as you can see, and a lot of submission for the challenge. There was a prize for also this challenge. So that's the data set I'm going to use, and that's the use case, is to basically find the ships in the satellite images. A lot of people wants to find certain things in the images. So for that, I'm going to use the image segmentation machine learning model today. And let's just quickly look at the data set that it has. As I mentioned earlier, it has a lot of about 200,000 files of satellite images. When you install this in a container, run this container, I'm not downloading all the 200,000 images. It's only a few images, so you can run locally. But when you run at scale, you can use all 200,000 images if you want. And I'll show you both running locally as well as running at scale in the cluster environment. And then this also has so it has images, as well as there's another CSV file which has a masking information, like where the coordinates for the ships in that particular image. So they gave some training data set where they will tell you in that particular image where are the ships, and they provide the coordinates for those ships in that particular image. So that's the two data sets we have. One is like all the images plus a CSV file, which gives you the masking information, which tells you the coordinates for the ships in those particular images, so you can train your model. Okay, so that's kind of data set I'm going to use, or this is the use case I'm going to use for my workshop. Let me just quickly check if there are any question. Thank you for putting that link over there. Thanks a lot, Jen. Okay, so let's continue. And when we train this model for image segmentation, I'm using this also open source version of model, this Python library for use for the image segmentation. It is based on PyTorch. So for this demo, I'm going to use PyTorch and PyTorch Lightning. And this is the segmentation model, the Python library that I'm going to use. Again, for everything used for this workshop is open source, so you can run freely locally on your laptop or wherever you want to run at scale in your cluster also without buying any software. Okay, so let's go back here. So once you have the container up and running, again, it will, as I mentioned earlier, it will provide 3 different containers. So one is the Jupyter Notebook. So here, if you are familiar with the Docker environment, it will tell you that it will provide the port to go to the Jupyter Notebook or different containers, the ports which are open. So in this case, this is the port for the Jupyter Notebook. You can either click from here and go to the Jupyter Notebook environment, or if you go back to the instructions here in our samples, just click on this link and it will open your Jupyter Lab environment. So again, everything is running locally in this case. So if you see here, the IP address is local. And here, if you go inside this, there's an image segmentation notebook, which I'm going to use today. And there's another notebook which we run during this demo, which is the setup required for this. So I'll come back to this setup later. And just explain in terms of the target architecture, like what architecture I'm going to use, or how I'm going to train this model, what tools I'm going to use. So we'll take this data set, the images, as well as the masking information, convert into a delta tables. Again, delta table, I'm using the open source version and not the Databricks. But if you want to run at scale in cluster, you can run that in Databricks environment if you want to use, or you can run in your own Spark cluster or the GPU cluster you have. So I'm going to convert those images and the masking information into delta table. And then, as I mentioned earlier, I'm going to use PyTorch and PyTorch Lightning to train the model and to feed the data set from the delta table to PyTorch. There's an open source library called Petastorm, Python library Petastorm, that's I'm going to use to load the data from delta table to PyTorch. And all the experiment tracking will be done using MLflow. And the for version control, I'm going to use LakeFS. And here there's some links here if you want to. There's information on, like, I got a lot of this information from Databricks blogs. So if you want, you can just read more about this, how you do the deep learning with PyTorch, Lightning on Databricks, and also this example, image segmentation with Databricks, the example I mentioned earlier, the use case, it explains a whole lot of detail here. So that's what I'm using it here. But you don't have to use Databricks. It is just the example that I took it from Databricks blogs and then implemented to run everything locally in this container. Okay, let me just take a pause here and let me check if there's any questions. Okay, thank you for putting the link there. Let me also, this segmentation one, let me also put the link for the Airbus challenge one. So let me get that link. And I'm going to post that link in the Q&A section. Okay, let me go back to my presentation again. Let me share my screen. Okay, so now back to this notebook. Let me increase the font size a little bit so it's easier to see. Okay, so far it was all the setup. So just let me repeat what I did so far, and then I'll walk through the use case. Uh, so first you go into the LakeFS samples repository. This is image segmentation local example. Within that LakeFS samples, there are a lot of other samples. You clone the repository locally, and then you run in the Docker Compose, run this workshop or tutorial in the Docker Compose in a Docker environment. And we have 3 Docker containers here. Mainly one is the Jupyter Notebook, LakeFS, and storage MinIO, which I'm using. So you don't have to use any third-party storage. Everything is bundled in this container group. And using the images from Airbrush Challenge. So again, it's an image segmentation model that we are going to use. And this is the, once you go into Jupyter Notebook environment, just open this image segmentation notebook that I'm going to use. Okay, so let's walk through the how the tutorial or workshop will work. So we are going to create the version control everything in LakeFS. So in LakeFS, let's say you start with the main production branch. LakeFS very similar concept as Git repository. So you have main branch. So here you can create a separate branch to run your local experiment. And if you want to run in a cluster distributed environment, you can also create multiple branches, and I'll show you that piece also. So let's first start with the local, like running this locally. A lot of time you want to build everything locally, train everything locally before you run this in a GPU cluster or before you run in the Spark cluster, whether it's Databricks or something else. So you want to run everything locally. So LakeFS will work in both the environment, not just the local, but it will work similarly in the distributed environment also. So we can version control all your experiments that you are running, whether locally or distributed. So once you create the branch, what we'll do is if you are familiar with the medallion architecture, so we are going to follow that, like bronze, silver, and gold data set. So what we are going to do, we'll take this images, satellite images data set provided by Airbus, and then we have the masking information. If you are running locally, you can run with MinIO, which I'm using, but if you want to run in the distributed environment, you can run using your online cloud object store or any on-prem object store that you have, which can interact with the distributed cluster. So in this case, I'm going to take images which are stored in MinIO locally, as well as the image mask, convert into a delta table. So we'll take that, we'll take a smaller data set because we don't want to use all 200,000 images locally. Sometime in your real environment, you will have petabytes of data. You don't want to download the whole thing or clone everything locally into your local environment. So you'll take the smaller data set, convert into a delta table first. So we'll create the bronze data set, and then we'll resize the images. We'll also transform the image mask into the actual image. So the image mask is a CSV file, which gives you the coordinates of the ships in the satellite images. And then we'll transform that mask into build a black and white images, and I'll show you how it looks. So that will become my silver data set. And then we'll join the actual satellite images to the masking images to see like how where the ships are in that kind of in satellite images. For example, in this case, this is my satellite images, and this is the image converted from the image mask. So in the image mask, it provides the coordinates for the ships. So for example, in this case, in this particular image, there are 4 ships here. So we'll join these 2 data sets to create the final gold data set, which will feed into PyTorch Lightning by using this pattern storm library to feed into that to run our model. So this is basically a lot of time people run the data pipeline to clean their data set before they feed into their model. So that's what I'm trying to replicate here. Basically, you are running different transformations, different changes to get it to the final data set and then feed into your model. And all these different versions of the data set will be maintained in LakeFS. So anytime you make any change, you can commit your changes in LakeFS and you can tag it. Like, for example, tag it as a bronze data set, tag it as a silver data set for my experiment X, Y, and Z. So anytime you want to refer back for ML reproducibility purpose, you can refer that data set by using tag. So you can say, give me the bronze data set for my experiment 1 on that particular day. So that you can go back anytime and refer that in that data set. In that case, as I mentioned earlier, internally, we are not copying the data. We just maintain the pointers to different data sets. So if we, without using LakeFS a lot of time, you will end up copying the data set. You maintain in different folders and different versions and different types of data set. But in our case, because we maintain pointers to those files, we don't copy any data set. That's how you will save the storage cost. Okay, so that's kind of high level, like how this notebook runs, like all the different steps that we are going to run through in this workshop. So I'm going to pause here and see if there's any questions. No questions so far. Let me see here. Okay, let's continue. Let me share my screen again. Okay, so here, everything required for this workshop, all the code, everything is included in this notebook here. So let me just quickly show how LakeFS looks like. So LakeFS is very similar kind of thing as a Git repository. So here you can create your repository. You can create the repository using the LakeFS UI. Again, this LakeFS is running locally in a container, as I mentioned earlier. So this is the URL to go to LakeFS. Or you can just, if you go to the Docker desktop and just click on the link here, and it will straight away take you to the LakeFS environment. So here you can create the repository from the UI, or you can also create using the API. So when we use Jupyter Notebook, I'm going to use the Python client or Python library for LakeFS to interface. But you can use REST API, or if you use Scala Java, you can use the Scala Java API also, or you can also use the Scala interface also. So you can create the repository. So first in LakeFS, you create the repository. You can create the UI here, for example, or through the API. You define your main production branch. Some people want to call it master or main or production, whatever you want to call the branch name, which is your main production branch, and where you are going to store your data set. So what's your storage? Where are we going to store the data set for the LakeFS repository? So let me explain. There are two storage locations you'll have. One is where your images or the training data set is stored, which is can be in a separate bucket. And this is where this storage namespace is where your LakeFS repository will be stored. So LakeFS, as I mentioned earlier, it maintains all the metadata. So that metadata will be stored in this storage bucket, for example. So everything is stored in your object store. Even your data set will be stay in your object store. All the metadata that LakeFS creates, that will also get stored in your object store. So everything stays within your boundary or within your VPC, within your storage. So we don't store anything in LakeFS. So, and if you use LakeFS Cloud, we just run the LakeFS server, but the data will be stored in your object store if it is S3 or something else. Again, just repeating that LakeFS doesn't read or write any data set, doesn't store any data set. We just maintain the metadata or pointers to those files. And that pointers metadata is also stored in your S3 bucket or in your object storage. Okay. So now let's go back here. So now I'll run through this notebook. Let me increase this font size a little bit here. So first, I'm going to define a couple of variables here. Define the repository name that I'm going to create. And if you want, you can change the repository name when you want to run it locally. You might create multiple repositories, so you can have run with different repository names. And then next thing is I'm going to run some setup information here. So a lot of functions kind of and different variables I'm going to run through setup, and that setup notebook is also available here if you want to look into all the detail. What setup I'm doing is in this case, like for example, where is the LakeFS endpoint and credentials, as we are running everything locally in a container environment. So all this information is already filled in, so you don't have to change or anything. But if you want to run LakeFS in your server or LakeFS in the cloud, you will change this endpoint to point to the LakeFS environment and the access key and secret key. So I won't go into too much detail on this setup environment, but you can look into that on your own. And if you want to change anything, you can change anything in this setup. But for time being, when you run this locally as a sample, you don't have to change anything in the setup, just run as is. So what it does internally in the setup, it will connect to the LakeFS environment, verify that it can connect and the credentials are right, and then it will create the repository, this local image segmentation local repository in LakeFS. So if I go back here into my LakeFS UI and just refresh this, so now we have just created this LakeFS repository. Again, in this case, it points to this storage namespace, but I'm not using S3. Everything is stored in object store min.io, which is also running locally. So if I go into my min.io environment, and it is stored in this, if you see here, S3 example. So if I go into the example bucket here in min.io, this is my repository information is stored here in this object store. So don't think that you have to use S3. It's just only thing is in this case, I'm using S3 compatible min.io object store. So this is my repository. So again, this looks very similar to like Git kind of repository. So here, when you go inside this repository, and I created with the main branch, but you can have master branch or production, whatever you want to call it, the branch name. And within that, right now, this repository is empty. There is no object here. To bring the data set into LakeFS repository, there are two ways you can bring the object data set into LakeFS. One is by using import. So let's say you already have your data set in a separate storage, you can just import from that. So when we import, we don't copy the data set. We just get the pointers to those files. So let's say you have millions and billions of files into a separate bucket or separate storage, you can just import from there. So, and that import process will take a couple of seconds only, because we are not going to copy any data into LakeFS repository. We are going to just get the metadata to those files which are stored in a separate storage. So you can import that, and I'll show you how the import works in the demo. And you can also upload the object. So when you you can basically from your local, if you want, you can upload any information, any file data set you have. You can upload that into LakeFS. But when you upload, you're basically copying that data file into LakeFS repository, and that data will be stored in the object store where the LakeFS repository was created. So it will be stored in this bucket when you upload any data set. Again, the data, everything will stay in your object store. LakeFS is not storing any data. So this is also your storage, and any data set you that import is also stored in your object store. So everything will stay in your object store. The only thing is there are two separate buckets here. One is to store the LakeFS repository, another is to store your original data set. And when you upload that file, data set will go into the object store where, or in the storage bucket where the LakeFS repository is sitting on top of that. So, okay, so that's so right now this repository is empty, and during this notebook, when I run the notebook, I'll show you how to import the data set. And then you have similar concept as Git, and you have uncommitted changes. And then you'll commit your changes as you bring new data set and commit the changes. So far, I just created the repository a few minutes ago. There's nothing in there, and this is the commit information at the time. Right now, everything is empty, but that's the commit ID that when you create this repository, and you'll see that as we do more commits, you'll see the new commits ID created. Then we have concept of the branches, like you have a main branch. For example, when you create right now, there is no data set in the main branch. And then we also created an empty branch also. Then I mentioned about tags. So anytime you commit any changes, if you want, you can tag that. So instead of using the commit ID, like the long commit ID here, you can use the tag to refer to any data set. As I mentioned earlier in the presentation, like you might have bronze data set, you're running multiple experiments. For each experiment for different data set at different point in time, let's say bronze, silver, gold, you can tag all those things. So later on you can refer it by tag, and that's what we'll do that during the demo, and I'll show you how it looks. And you can compare different branches, so you can see what data change between the two branches. So let's say you are running different experiments, you can want to compare, like let's say my model performed well for this branch or this data set, and I want to compare with another branch, another data set, and see what the difference between the data set is. So you can compare those two branches or two commits anytime and see what data changed between those two commits or two branches. And I'll show you that how it looks during the demo. And then we have Git, similar to Git actions. We have LakeFS also has actions concept or hooks. So anything, if you want to do a kind of CI/CD process, continuous integration, continuous deployment, you can create the hooks in LakeFS or actions in LakeFS and automate a lot of process. For example, before you merge your changes into production, or before you commit any changes, you want to do some data quality checks before you run your data is fed to your models, so that you can automate those things using the hooks or actions. And you can use any third-party tool for data quality checks, or you can write a script. In this case, either we use Lua script. You can do all those data quality checks or any checks you want to do using Lua script. We're also coming out with the Python script integration also. So you can run your actions using Python script also. And then quickly look into the settings here. So here, as I mentioned earlier, we have garbage collection process. So we'll keep your storage clean. You can define your retention policy, whether how long you want to retain that data set for the production branch, for let's say experiment branch, and then also sometimes you want to protect your production branch. You can protect your production main branch also, so nobody can directly write to the branch. So this is how the LakeFS UI looks. Let me stop here and see if there are any questions. There's a question, where can I find the last slide about the process of the project? Again, if you go into, yes, somebody shared that. Thank you, Edgar. So yes, this if you clone the repository, or if you go to our Git repository, you'll find all that information there. Thank you. Okay, so let's share the screen again. Let's go back here. So now what I'm going to do, just create the repository. Right now, as you can see, everything is empty here. And we provide the LakeFS integrates with Git also. So sometimes people want to use Git to version control their code, like model code. and use LakeFS to version control the data set. So we have integration with Git. So you can use Git for version controlling your code and LakeFS to version control your data set. So what I'm going to do is I'm going to create a Git repository also. Initially I create the LakeFS repository. I'm going to create the Git repository here. So when I create this here, you'll see it will create a folder set here. So now I just created the Git repo here. Right now the Git repo is also empty here. Now let's start. Okay, so the next thing is creating an experiment branch. So right now we don't have any data set in LakeFS. Now I'm going to create a experiment branch, bring my data set into that experimentation branch. So as I mentioned earlier, I'm going to use the LakeFS Python client to interact from Python to LakeFS. So in this case, I'm going to define my experiment branch. I'm going to run the experiment branch 1 and connect to the LakeFS. And if the branch already exists, it will just say branch already. It will just skip that. Otherwise, it will go and create the branch in LakeFS, as well as create a branch in Git also. The same branch in Git repository as well as in the LakeFS repository. So let's run this. So now here Git, and for the Git repo, it switched to the new local experiment 1 branch. And now we also created this branch in LakeFS. So if I go into LakeFS branches, so now we have this new branch here. Again, and this branch has same commit ID as the production branch. Right now, the production branch is empty, but normally, even if you have terabytes and petabytes of data in your production branch, when you create a new branch, it will be a millisecond operation to create a new branch. Again, we are not copying any data, it's just set of pointers we maintain. And when you create a new branch at that time, it will be the same commit ID as the main branch. I'm creating this new branch from main, so it's the same commit ID until I change anything in this particular branch. Okay, so now we got a separate branch. Now I'm going to import the images. Again, for running this locally, I'm not going to import all 200,000 images. In this case, I'm just imported 50 images only. Again, when you import the images, we are not copying any data. We are just getting a set of pointers to that images. So in this case, let me show you here how it looks like. Our sample data is stored here in this Airbus challenge here. So all these images are stored in this folder here in this object store. So that's where we are importing it from. Again, I'm not copying any data set. When I import the image, it's just creating the set of pointers. So now if I go into my LakeFS repository and refresh this and select this, now you'll see that commit ID has changed because in this particular branch, I just imported those 50 images and committed my changes. So now it's a new commit ID. And if I go into my this branch, I just imported this raw data set. This is my CSV image mask, and then also this training data set. So let's look into the image mask. Again, if you want to see where this data points to, the metadata about this, you can look into the object info here. And this is my path for that actual path here, but this is the physical address of the file. So this is stored in this min.io, in this case, in the sample data, which is over here. If you can see sample data and Airbus detection and the training data set too. So that's where the file is stored here. So again, we are not copying any data, it's just a pointer to that file. So that's why even if you import millions and billions of files, it will be just in a couple of seconds, you will have all those data set available in LakeFS repository. And let's dig down into, again, this is image stored in my training data set here in min.io storage in this case. But when you click, it will go and fetch that data set or read that data file from that storage. Again, we are not storing anything. Everything is stored in the main bucket. It's just a set of pointers to that file. And so let's continue. So here, so I just imported those 50 images to run locally. But when you run in a cluster in the scale, let's say in distributed cluster, then you can import all the 200,000 images. And I'll show you that code also. Now, let's say I want to run, right, so far, my LakeFS repository and everything is stored in MinIO storage. But let's say I want to work locally. So you can clone locally. In this case, as I mentioned earlier, I'm going to use the LakeCTL, which is a command line interface for LakeFS. So you can see LakeCTL clone locally to that repository, then a particular branch. And within the branch, you can specify a path. So what it will do is it's going to clone this or copy that data set locally on my in my container, in this case, or locally on my laptop. So when I copy this, so now it's copied this into my local folder here. Again, this is a raw data set. As you saw earlier, we have the masking CSV file, as well as all those images that you saw online. So now I have my data set locally, so I can work locally if I want to. So that's what I just did, clone locally. One thing I mentioned, like we earlier, that we integrate with Git. So we work closely with Git, and in Git, you'll version control your code, and in LakeFS, you'll version control your data set. So the way we keep track of all this thing is in Git repository. If you see here, I cloned this data set locally to my Git repo, but we don't want to upload that huge data set into Git repository. Git cannot handle the huge data set. So what we do, we automatically create a Git ignore file. In the Git ignore file, we automatically add that information that ignore this this path here, which is LakeFS local. So anything inside this, including the images, will not be uploaded to Git repository. Except there's a YAML file which we maintain for LakeFS reference, where it will have the what commit ID was used for that at the time for when you clone it to the when you commit to the Git repository. So if I look into this YAML file, which is stored here, you can see it maintains the data set, what is the source, in this case, the repository name, the LakeFS repository, and the branch name, and the commit ID, which I'm currently using for my data set. So again, so in Git, we'll upload this information. So anytime in future, you can go back and refer to this commit ID or this source URL to refer to that particular data set. So that's how we integrate with Git. I'm just going to pause here and see if there are any questions. So there's a question: if you edit a file, for example, add a row to a CSV, will that file get duplicated in my object store? Yes. So anytime, if you know the object store, in object store, you cannot update a file. You basically delete a file and create a new file whenever you make any changes. So basically, object store is immutable. So that's what we are also doing, the same thing. So anytime you edit a file, basically it creates a new file. So with the new information. So your main production branch will be pointing to the old file, and any changed data set in that new branch will be pointing to this new file. So yes, the question becomes like, over times you might end up having lots of files or duplicate files, but those are not duplicate files. These are different files or the change files. And using our garbage collection process, you can automatically clean your storage or clean those files. So you can define your, as I mentioned earlier, retention policy, how long you want to keep that data set. And then garbage collection process will automatically clean your storage. Okay, so let me try to rush quickly so we can complete everything. Thank you. Okay, so now I got my local data set. You can change the data set locally? That question was very relevant for right now. So I'm going to do is I'm going to delete some images which are smaller than 100K and add few new images. So sometimes people change, and so any changes you would do, in this case, I'm doing it locally, but you can, then I'm going to commit to the LakeFS also. So in this case, you'll see that I added these files here, removed some of these files. Anything is smaller than 100K in this case, for example. So all these changes we committed to. So I did all these changes locally here, if you can see the source here. But we also committed to the LakeFS repository also. So anytime if I go back to my LakeFS to that particular branch, you'll see the latest data set also available in LakeFS. So that's how you can collaborate with your team members. So any other team members can go back and refer to that data set. And let's next thing, I'm going to add changes to Git repository and perform the initial commit. So in this case, just I committed the YAML file to Git repository, and I'm going to commit my local changes to the LakeFS repository. So we did two commits. One is in the Git commit, another is the LakeFS commit. And here you can see how many files were uploaded or removed. In this case, as you see that there were 4 files were added and 2 files were removed. So now if I go back and refresh my branches here, now I have my new commit ID. And also now I'm going to verify and read my data set. So I'm going to read from my local files here, all the images. So again, I'm using a Spark in this case and read my images. And in this case, just getting the metadata information about those images, the path, location, and the width and height of those images. So in this case, as you can see, everything is stored locally on my local environment here in this container. That's what I'm going to use local files for my training my data set. Next thing, I'm going to run that pipeline, transformation pipeline. As I mentioned earlier, you have branch data set. So I'm going to convert these images and the masking information into a delta table, create my branch data set. And then, so everything I'm going to do locally, then commit into LakeFS repository. So everything is also stored in LakeFS repository for versioning for that. And also I'm going to tag it so you can refer it back later. So commit to the LakeFS repository and tag it also. So my bronze data set, then I enrich my data set and create my silver data set, and then so on. So finally, I have created my images mask also, CSV file into images, masking image, and transform everything and store everything local. Do all this pipeline transformation locally, but also commit into LakeFS repository. So after each step, I'm just committing into LakeFS repository. So this is finally how our goal data set looks like. So we took that CSV file, that masking information, converted into black and white images. And this is the relevant same actual satellite images. So it will show you where the boats are in this image, for example, these 2 boats over here, and so on. So this is just to visualize that data set, how the final data set looks like. And now if I go into my LakeFS repository, I can see that data set also committed here. I can go back and refer anytime with the tag, as I mentioned earlier. So in this case, I have my bronze images, my bronze mask image, masking data set. So anytime I can refer back to this tag instead of using the commit ID. You can use the commit ID and refer the data set by commit ID. When you read, you can specify the repository name /commit ID, or you can specify the tag name instead of using the branch name. So that's how you can refer back to any previous data set you want to. Okay, so next I'm going to take this gold data set and convert into training and test data set. So by using 80-20 rule, most of the people are familiar with this who run the ML. So in this case, I'm just using my gold data set, final data set, convert into training and test, and then use petastorm library, as I mentioned earlier, to load this data set from my delta table into my PyTorch model. So that's what here it is doing. Next thing, I'm just going to train the model. Again, everything is running locally. So in this case, specifying a certain parameters to train the model. There are 3 parameters we are using here. So in this case, these are the FPN architecture. So you can read more about this image segmentation model and the different parameters which are used to train the model, and what's the final output metric will be. In this case is the interaction over union, like where the boats are in the satellite images, and what's the metric value for that. So when you are training locally, you might train with a few parameters. In this case, I'm changing some, training it twice here and running it twice that. But when you run at scale and in the clustered environment, in the GPU cluster, you might run thousands of experiments with different parameters using hyperparameter optimization, and I'll show you that also in the end. So I just quickly ran these tests. Ran this model twice. So for this, I'm also using MLflow to keep track of all the experiments. So if I go into my MLflow, this is the MLflow is also running in my Docker container in this port number 5002. So you can see that here. So if you click on this, it will take you to the MLflow. So now I just finished running these 2 experiments. So let me refresh here. So you can see just ran these 2, and what the metric was used, what was the output for the metric output, or what was the data set that I used. So here we, when you use LakeFS, we add a lot of tag here. In this case, for example, the branch name, the repository name, and what data set was used. And anytime you can open this experiment, you can get what data set was used. In this case, I've used the gold data set. You can click on this. It will provide you the information about the gold data set. And these are my parameters, which I use to train my model. And this is the metric output. And also we add a lot of information we add here in the tag, including the data set which was used. So if this LakeFS data set in that particular, the repository, you can just copy this link. So if you copy this link, it will straight away take you to that particular data set which was used to train that model. So again, this data set was just created, and these are the files of this data set was used to train that particular model. So going back to my notebook here, so now let's say in this case I ran 2 experiments, and based on the metrics I can specify which is my best run. So so I can specify what's the best model based on the output parameter. In this case, IOU, interaction over union metric, which I'm using to find the best model. And then I can save this best model information in LakeFS repository. So I create this best model text file, upload it into LakeFS, and also I can store my notebook, this code, my image segmentation notebook, as well as the setup notebook in my Git repository. So that's what I'm going to keep it here in my Git repo. So if I just run this command, so you'll see here now, now I have my code in the Git repo. Again, the local data set will not be kept uploaded into a Git repository. That will be only stored in LakeFS repository. But we provide the tight integration with Git. And then to run this MLflow, again, there's a notebook here, which you can open this and just run this to start the MLflow server. I already ran ahead of time, so which is MLflow already running. So all the instructions are provided here. And then also it will, when you run the last cell here, it will take you to the commit page in LakeFS. Also, what data, like this is the last commit we did. We uploaded the best, like information on the best model. Again, when you commit any changes into LakeFS, or when you upload any object into LakeFS, you can include a lot of metadata also. So like, for example, when I committed this best model, I can include the output metric as well as the model name, the run name, which you saw in MLflow, and what was the model version, and the git commit ID also. Like if you are tying the git to LakeFS, you can keep the git commit ID. So in git, we are keeping the LakeFS commit ID, and in LakeFS, we maintain the git commit ID. So you can include as much information as you want in your metadata, and you can search that metadata also later on. So here, this is my best model information here, so which includes all the information, all the metrics that were used to train the model, what data set was used to train the model, what code was used. So everything is included here in this file. And again, from here, you can also straight away go into the MLflow from here. So this is my best model which was run. So again, I can go into that best model and see what parameters were used, what metric output, and the tags, what data set was used to train this particular best model. So this is like running everything locally. Now what you want to do, you can take the same notebook, and let me pause here before I go any further. Let me see if there are any questions. No questions. So let me go back to my share my screen locally. Everything, including the training your model, running your model, everything was locally. But if you want to run the same model, same thing, in distributed cluster in GPU server, you can do that. So here, if you look into this image segmentation setup, there's a way option to enable the GPU, but currently I'm not using GPU locally, but you can, if you want, you can enable the GPU also if you want to run in the GPU cluster. So I'll show you how it looks like. So if I go back to my presentation here, so the first thing you saw was running everything locally, but now what you can do is you can run this in the distributed fashion. So again, your data set will be stored in LakeFS, and then you can create a separate branch to run that in a distributed, and you can run multiple branches, create multiple branches to run in distributed fashion. So same, there's another sample here, which is same notebook, but which works locally as well as in the distributed environment. So you can use that. Again, this same image segmentation example. So here, in this case, I ran in Databricks cluster, but you can run in any GPU or Spark cluster you have. So I'm just skipping all this. You already saw this, the whole code. Here, one thing I forgot to mention, that you can specify how you are running. In this case, whether you are running in the local environment or you are running in the distributed environment. So if you're running in the cluster with hyperparameter optimization, you can specify distributed. And when you use distributed, you can load, let's say in this case, for example, all 200,000 images. When we are running locally, we are using a smaller data set. But here you can specify, let's say, images per experiment, let's say 10,000 images per experiment you want to run, or 100,000 images per experiment. So you can change those parameters here in this notebook. And I'll show you quickly here. Earlier, we ran this model like twice only, but here I'm using HyperOpt for hyperparameter optimization. So you can run with different parameters, lots of experiments. So in this case, I'm using Databricks cluster. So you can run lots of experiments. So if I go back here into my Databricks environment, the same notebook, same thing I ran here in my Databricks environment. This is my, again, connecting from Databricks to LakeFS. This is my repository name, for example, and so on. So everything is same as you ran locally, just run locally, and once you are done, then you can run this in your distributed cluster and run using the different parameters with lots of experiments. So if you go into LakeFS experiments tracking, which is also uses MLflow behind the scene, you can see all the different runs I did. I did only a few runs, but you can again go back into any of individual runs, and you can see what parameters were used. what was the metric output, and what data set was used. So I can just look at this. This was the data set used, so I can just copy this link and then go to my URL, and it will straight away take me to that data set which was used to train that model. And again, I'm using this tag here, as I mentioned earlier. You can tag anytime, and then you can refer it by tag. So in this case, I'm referring it by my tag name here in this URL, if you see. Again, there are lots of different tags. So anytime you want to go back, you can refer the data set by different tags. And all these experiment tracking, everything is stored in ML flow, so you can see what data set was used to train that particular model. So just to just explain again, like what we did overall. So first we train our model locally using LakeFS and maintaining the version control in LakeFS. But you can take the same model, same notebook, and run in the distributed environment to train against the larger data set. In this case, 200,000 images, and track everything in LakeFS repository. And anytime you want to refer back, you can go back and refer to that data set, just going to any of each experiments and then referring it to that particular data set. I'm going to pause here and see if there are any questions. Okay, so we have some time left, like around 10 minutes left. If you guys have any questions. Meanwhile, let me share a couple of other things. So like what's the benefit advantage of using LakeFS other than that just the version control? Like it saves your storage cost. A lot of time when people are running lots of experiment, they make a copy of the data and they have different folders, different copies, and people forget to delete the data, and then the storage just keeps on growing. So using LakeFS, because we don't copy any data when you create a different branches or different data sets, so that saves a lot of storage cost, as well as historical data. We automatically clean it based on your retention policy. We'll go and clean any storage or delete files from the storage. So that's how you basically save a lot of storage cost. And also for testing time reduces by like 80%. Like if you're running lots of experiments, doing lots of tests, you don't have to copy or manage all your data sets. People will spend a lot of time on doing that. So that will reduce your time to spend more on building the model and training your model than managing your data set. And also, like if you want to go back, you can easily go back to the any historical data set. So let's say you are doing any transformation, make some changes in your data set, but you made a mistake, you can go back and revert back the changes. Now, I did not show that in the demo, but there's a revert command. You can go back into history of any data set. And if you want to reach out to me, like you can talk to me on Slack. So if you go to lakefs.io/Slack, and you can join our Slack channel. And then if you have any questions, you can ask that on our help channel, or also you can reach out to me directly on Slack too. I'm also available on LinkedIn if you want to reach out to me on LinkedIn.